All right, I think we can start. So, hello everyone, welcome to episode 22 of Warsaw.AI meetups. My name is Pavel and I'll be the host of this event. And this event is organized in collaboration by the Quantum AI Foundation and Ideas NCBR. And our partner, strategic partner, is Allegro Tech. So we are very grateful that we can organize this event here in Allegro for the next time. And one more important thing before we start, we encourage you to subscribe to our weekly newsletter, Warsaw.AI News, if you haven't done it yet. So we can stay up to date with our events and the news from the AI world. But now it's time to start and to announce our speakers. So we'll start with the presentation given by Jakub Fajkowski and Dominik Filipiak. And it will be about polite teacher. Then Michał Turski will tell us about table generation framework for Encoder-Decoder models. And finally, Michał Daniluk will tell about Synerise BaseModel, a foundation model for behavioral event data. And finally, we'll have after party with networking. So if you have time, we encourage you to stay with us for the after party as well. All right, Jakub, Dominik, if you are ready, we can start and the floor is yours.
All right, hello, welcome. Thanks for having us. So we are here to present joint work of AI Clearing and me from Berlin, and also a lot of actually other people as well, not being present here. So we are very happy to present. Especially, we are very happy that we can present with our recent work, which was recently published. And I'm Dominik. So I work now as the CEO of a Polish branch of Berlin, advanced AI consulting company. But this was actually a work which was done mostly during my tenure at AI Clearing, where I was the lead AI researcher. Yeah, that was a fruit of my time at AI Clearing, and Jakub is here from AI Clearing, so maybe that's a good moment to.
Hi, my name is Jakub Fajkowski, and all of you who were waiting to see Adam Wiśniewski, which is our CTO at AI Clearing, I'd like to apologize in his name because he wasn't able to do it today. And I am leading an AI team at AI Clearing. Our product is about drone construction management platform. So we have a really cool product, and yeah, the core motivation for this whole paper and this research done in AI Clearing was mainly because we were a pretty young startup 3 years ago. We had some clients, but not a lot of data, and we had an idea to develop this platform for visualizing the data from drones taking photos all around the construction site. And on this platform, you could monitor such stuff as progress, construction deviations, schedule deviations. For example, this is great for our customers if they want to release payments to their subcontractors to control whether all of this stuff is happening in accordance to design. Yeah, the scale was pretty small, and we wanted to scale this up using artificial intelligence. And all of this reporting required knowing the shape and precise location of the construction items on those construction sites. So, as I said, we had a small amount of data, small amount of labeled data, and we kept receiving more and more drone images that we would like to use in the training, but only the small part of those were labeled. And you can see the screenshot from our platform. On the red mark, you can see the deviated pipeline marked on the orthophoto map. And on the with the blue line, you can see the desired location of this pipeline. So yeah.
Right, thanks. So business motivation is pretty clear, but actually I want to present the research motivation. So this is something which is super interesting for me as a researcher. But before doing so, well, this is my very first time speaking here, and obviously super stressed. So I almost forgot to mention all the people who also contributed to this work. So Andrzej Zapala, who is here representing Warsaw University, Piotr Temczyk from multiple organizations, currently NASK, Anna Fensel from Wageningen University, and Professor Cygan from University of Warsaw. So that was the business motivation. But what's the research-wise perspective? Well, first of all, perhaps all of you know very well that deep learning is expensive. It's expensive in many ways, but let's leave all those like computational costs aside for a moment, or like hardware constraints. And it turns out that like, quite often, most of the cost or time is consumed by the data itself. So yeah, getting the right amount of data is expensive, but actually it's not about the data. Because in many domains, like in vision, for example, it's relatively easy to get the right amount of data. The labels are the problem, especially when we are talking about pixel-wise labels, like in semantic segmentation. So that's super problematic to get, especially if your label is kind of, you are not telling cats from dogs, but for example, you need to distinguish different types of asphalt as in the construction industry, right? So it's not very easy to, for example, hire people on Amazon Mechanical Turk to do it. So the problem is that we get a lot of data, or like the right amount of data, but we don't have enough labels and we can't produce them quickly. So semi-supervised learning to the rescue. That's our paradigm, which we will be working on. And more formally, semi-supervised instance segmentation, because that's the task we are tackling here, consists of two elements: instance segmentation and semi-supervised learning. So instance segmentation is a computer vision task which jointly combines object detection, which is all about localization of instances, and semantic segmentation, which is basically a pixel-wise classification. Then, on the other hand, we've got semi-supervised learning. So that's the setting in which we are. We got the right amount of data, but only a fraction of labeled. So what can we do in this scenario? Semi-supervised instance segmentation to the rescue. So for those of you who are like a bit more like visual learners, that's instance segmentation. So basically, we got like a pixel-wise labels. We can tell where's Xena and where is the background, and we also get like instance bounding boxes, which separates separate instances of a person class in this case. So that's a visual representation. How about semi-supervised learning? What is it? Well, basically, it's in between supervised and unsupervised learning. The difference is in the available labels. So in supervised learning, you got all the labels, right? Easy. In unsupervised learning, you got no labels at all. And in semi-supervised learning, which is in between, you've got, well, typically something in between 1 and 50% of available labels. And in this condition, this is the condition at which we will work in. So we want to present polite teacher. This is the method which we would like to present. And that's a kind of a simple method, which is based on very well-known teacher-student framework. And when we started this work, it was the very first work which was tackling the problem of semi-supervised instance segmentation, which was very well suited to our business setting. And we got a couple of ideas. So first of all, the first work in semi-supervised instance segmentation. Then we got also some ideas how to filter out noisy pseudo labels, which I will show. That was like stems from mask scoring. And all in all, we got kind of nice results because we improved the baselines in different semi-supervised regimes by around 8% in terms of mask AP. So what's the method? So basically, there is a two-step training procedure. In the first step, we train one network only with label data. So basically, that's supervised learning. The more interesting part is the second step, which is this mutual teacher-student learning. So we got two networks right now, which are jointly learned. And we also utilize pseudo labels. Both networks, teacher and student, receive the same labels, but they are augmented differently. So basically, we distinguish between weak augmentations and strong augmentations. So the weak ones are, for example, those ones which are randomly flipped. And in terms of a strong augmentation, that's some sort of a very visual perturbations, such as, for example, Gaussian blur. You can tell that's a very perturbed image. And most important thing, so since we are living in this semi-supervised condition, there has to be some sort of a pseudo labels, and predictions from the teacher model serve as a ground truth for the student model. So one model is producing labels on unlabeled data, which can be later utilized. And that's the architecture overall. So that's how supervised data are processed. We've got an input image X, which can be either strongly or weakly augmented. Then there is a student network, for which we optimize some sort of a loss function, and we got our result. The trickier part is obviously the second part, at which we have to deal with unsupervised labels. So we've got two networks which work together, and teacher is producing Y with a hat, which is our annotation for pseudo labels, and those pseudo labels serve as a ground truth for the student. So student is trying to estimate an estimate in another way, and this is trained by standard gradient descent. Yes. So it's copied, but it's like updated differently later on because it's basically a teacher is an exponential moving average of its students, and so this is kind of parallel to ensemble learning. One cool part, which is our addition, is thresholded gradient, meaning that since we are training our network on an estimate, well, there'll be a lot of noise inside. So we try to filter out noisy pseudo labels with threshold gradients. And a bit about the detector. So we use center mask as a detector. Basically, I mean, to keep it in short, is a very smart detector at which, instead of predicting bounding boxes as a object and four corners, you also predict additional thing, which is centerness of an image. And yeah, that's a very distinct architecture. It uses pyramid of features, and the outputs regression of a box, its classification, and centerness, which looks like this. So we are trying to predict centerness of a bounding box and the distance from the center. So we got an artificial ground truth for the centerness, but that's for a different lecture. And on top of it, you can add obviously a segmentation mask, which tries to label pixels on a detection output. So that's center mask. That's not our work. Our work starts here. How do we generate and operate on those pseudo labels? So a lot of them can be noisy. So we need to filter them out in a way. And basically, we got two ways to get them out. First operates in a bounding box confidence. So there's this notion of objectness in object detection, and we kind of treat it as some sort of an uncertainty measure or certainty of something being an object, which is used for thresholding. And also, we add a separate head, which tries to predict the IOU of a given bounding box. So this is kind of an additional head, which tries to assess the quality of a prediction. And this is also used for thresholding. So very simple method, in fact. In terms of optimization, that's very standard. So we train for supervised and unsupervised component. And the supervised component consists of classification, centerness, bounding boxes, masks, and IOU loss. And in terms of pseudo-labeling loss, we try to we are using only classification, masks, and IOU. So there is a bit of a difference here. And yeah, already talk about it, but in terms of a student, it is trained in a standard gradient descent, but the teacher is trained in a slightly different way. Basically, it's an exponential moving average of its students, and as in this teacher-student framework, the strength of a teacher lies in the diversity of its students. So, what about evaluation? So, thanks to AI Clearing, University of Warsaw, and perhaps few other institutions, we will able to conduct extensive tests. And yeah, basically we tested on different supervision regimes, 1, 2, 5, and 10% of available labels. And turns out that our method, compared to center mask, yield quite a constant addition of 8% in terms of, I mean, average precision. The oracle, which is like theoretically highest result, training on 100% of labels, is 70%. So there's only 4 or 5% of difference without using 90% of labels. So that's quite a nice thing. And yeah, in parallel to our work, there was one paper which attacked the same subject. However, those results aren't quite comparable because they use different data split, which were random and not published. So we can't possibly compare them to us. I mean, our results are a bit better, but that wouldn't be fair to say because it's a kind of apples and oranges comparison. Some qualitative results. So you can see, I mean, maybe it's not always perfect, but in terms of 1% data, you can already tell that the network is picking up. And for example, the cat in the middle row is being quite correctly detected. So that's images from COCO 2017. We tested for ablations, for influence of different hyperparameters. So binding box thresholdings work very nice. But one ablation which was quite surprising was this U-shape in terms of testing for IOU mask scoring head. And it wasn't clear whether it is useful or not. So we conducted another ablation, which basically compared network with mask scoring versus network without mask scoring. And you can tell it's basically learning much quicker. So there is a hidden added value. It's not always about the metric itself. The speed of convergence also matters. So there were 2 work which were concurrent to ours. The first one was already mentioned, noisy boundaries. And the second one, which is super new. So our method is no longer state of the art, sadly. So recently at this WACV conference, team from Facebook AI Research surpassed our results, which I mean their method was kind of similar, but they used more fancy first stage, which we call burn-in stage. But yeah, it's actually nice to see that it is developing. There are certain limitations to our study, but due to the time constraints, I won't go through them all. But basically, we would like to test on more data set than COCO There is no dedicated data sets for this kind of machine learning tasks, so one need to create a new one. So yeah, that was Polite Teacher. Simple but quite effective architecture for the problem of semi-supervised segmentation. And we demonstrated that we can get like five less mean average precision, but without using 90% of the labels, which is very relevant to many business problems. And that's all for in terms of a paper. So if you got if you got questions, I'll be happy to answer any of them. If you are curious, paper just got accepted to the IEEE Access, but the preprint is on archive. So if you Google for Polite Teacher, you'll get it. Very soon the code will be released, courtesy of AI clearing. And if you get any questions, those are our emails. We got like 2 quick messages to conclude this presentation. So maybe Jakub first.
Yeah, so I'd like to tell that maybe a few years have passed, but one thing didn't change. We are still looking for some awesome talents like Dominik himself, because yeah, we are still expanding and we have a lot of fun projects to implement. And we use great tools, Docker, Kubernetes, MLflow, this PyTorch, this kind of stuff. Yeah, so if you want to send an email with a CV, so this is the bottom email, JF.
Yeah, and obviously I can recommend AI clearing because been there, done some research, and it was super good time in my career. I, on the other hand, got a slightly different problem. So I have a privilege of working with super talented people at Perlin. But we are very open to new challenges. So if your company needs some good people, good AI consultants, whether good at strategy or actually doing some code, being capable of state of the art, we got great people like ex AWS or ex SAP alumni or multiple PhDs from University of Munich, that kind of stuff. And our clients are, for example, Deutsche Bahn or Carl Zeiss. So yeah, hit me up if you would like to do something together. So thank you very much. And yeah, we are here to answer your questions if you want. Thanks.
All right. Thank you very much. Thanks. Okay, so now it's time for a question, but also a message to people who are sitting at the end. There are still some seats here in front in the first row, so you can come here, of course. But now it's time for questions to our speakers.
I'm wondering whether giving the perturb data to the teacher is really beneficial because you perturb it only a little bit, or if it's just a little bit of noise that you could have inserted in any other place, and it doesn't matter that it's the teacher. That wouldn't it be better if the teacher really knew the perfect data at least?
So that's a very good question. I mean, it was tackled not by us actually, but the previous line of research. I don't remember correctly. I mean, not quite sure, but I think it was like from the research in a semi-supervised object detection. But basically, that's why you got this distinction to weak and strong augmentation. So very little noise is going to the teacher, whether in terms of student, we got a little noise. But yeah, so it wasn't studied in our paper. We were like standing on the shoulders of giants here. So that's obviously a very good remark, but we follow the other line of research here. So yes, thanks.
Good, thanks. Do we have more questions? Right.
So thank you guys for the interesting presentation. And from what I observed, you addressed the problem from the, let's say, method perspective. But I know we can also address the problem of small amount of reference data from, let's say, augmentation perspective. And there is a possibility to generate some samples either using generative AI or from the physical models. And there is a company, even I have listened to the podcast, it's called Encoder-AI. And I was thinking, if you have checked their offer, have you tried to compare, let's say, using their product as compared to your results?
So not sure. Thanks for the question. Not sure how much I can reveal in terms of AI clearing, and I will hand over the mic to Fajka in a second to answer this. But I can tell you what's the research perspective as a researcher. So I am aware of those methods, but I mean, if we are like racing for the state of the art in semi-supervised instance segmentation, like we are usually trying to improve the method itself, doing more fancier augmentation, or actually like using like new data. This is kind of like, you know, unfair advantage in competition. So obviously that has a great value in terms of moving things forward, but that will be like kind of different category of race. So we are focused on the architecture in this work. And I don't know, Kuba, do you have anything to add?
Yeah, regarding this generative data approach, the characteristics of the construction site is that you have a lot of standard cases, but we focus on detecting these non-standard cases, so these anomalies. And if you focus on the generative data, that you would probably get more of those standard cases. We tried some approach with synthetic data though, but this yields a little bit worse results than using real data. And also, yeah, we have a lot of unlabeled data to use. So this was like a natural evolution and motivation for this work.
All right. Last question.
Hi, thanks for the talk. Could you tell us, for example, what percentage of this unlabeled data were you able to label using your approach? So, because eventually you wanted to use it for the AI clearing, right, for the real data set. So what was the impact of your research on the business case?
So this is actually hard to measure because the modes in which AI clearing operates is there is no one single standard data set which is reused or ever all of the. I mean, it can some classes are like specific to the given construction sites. You know, I need to use those round words due to all the NDAs I'm having, but I would say it's not that simple, and quite often you have to deal with new classes which weren't present in a data set, and can't provide a single number because it varies on the use case. I don't know, Kuba.
Yeah, I think you addressed this quite good.
So sorry for not providing a juicy answer here, but it's actually a complex issue. So this method was created in order to help with trainings and improve the metrics on the training, but the performance varied on a different use case. So there is quite often there is no this standard model which says all the use cases can be, but yeah, AI clearing operates on many different modes of construction, and I guess that kind of gives it away, but guess that's a good topic to the discussion afterwards, maybe in private.
All right. Will you guys stay with us for the after party?
Yes.
Great. So if there are more questions, please ask Dominik and Jakub later during the networking part. And now we have to go to our next speaker, but let's thank once again Dominik and Jakub for great presentation.
Thank you.
Thanks. Now it's time for our second speaker, Michał.
Hi, I'm Michał, Turski, and I'm going to present Stable, which is our model for table generation or framework to table generation. I co-authored this paper with my colleagues from Snowflake, so another Michał, Łukasz, Tomek, Gabrysia, Karolina, David, and Łukasz. So let's start. What is it all about? Why do we even care about generating tables? So The main motivation is that tables are very useful form of knowledge representation because they can be you can be read by human as well as computers. So, for instance, any non-tech user is capable of reading such a table, but also so we can extract such a table from a simple sentence. But we may also store it, for instance, in a database. Yeah, but tables are very good to unify things. So, for instance, on an invoice, we've got a table per se. So there is a table, and we may want to extract it for some business purpose, but we may do some operation like skipping some columns, changing their orders because of layout of database, or so on and so on and so on. But for instance, on Wikipedia articles, we've got another kind of tables, which are tables of key properties in key value manner. And it would be nice to have a model which is able to summarize articles with this kind of tables. And we may also present other tasks like entity and relation recognition, which is one of NLP tasks in form of table representation. So our main motivation was to unify different tasks under this document to table paradigm. It's similar idea to what T5 did before, which was unifying different tasks under text-to-text paradigm, which led to large language models and other cool stuff we've got now. There is also one interesting thing about having data in form of table. So when we've got some sentence like he was born in Petrograd on January 15th, 1915 to Russian French parents, and we want to extract key properties. Let's say we've got a large language model which is capable of generating tables, and we want to extract 3 key properties: citizenship, place of birth, and date of birth. It's easy to extract date of birth. It's almost explicitly said, but let's say we want to normalize it. We've got a language model, it's able to do so, that's cool. Place of birth, once again, we are able to normalize it. But citizenship part is tricky because it requires reasoning. So it requires a date of birth because Russian Empire existed at the time, but not later. And place of birth and citizenship of parents. So in this example, we require a model to do reasoning over multiple things. And thanks to this tabular structure, we think that it's easier, and we proved, in fact, that it's easier for a model to reason over already extracted properties in the table to predict another values. So that's motivation. And how does our framework work? So let's start with some training example, toy example. So it's about toys. There are toys colored red, green, and blue on the table. The square is green, the triangle is blue, and the circle is in the remaining color. And we've got a gold standard, so expected output. And a classical approach people used before our research is linearized approach. So we train model to read table and to predict table left to right, top to bottom, as human would read it. But what we propose is different. It's a mess. We train model to predict table in any given order. So we don't assume table should be generated in some particular order. We want it to be predicted however the data guides the model. So how do we do it? Let's say we've got some decoding state. So three values are already filled: triangle, blue, and red. in this order. And on first epoch, we randomly pick that column to be predicted as next one. In second epoch, that column, and on third epoch, the third one. So over multiple epochs of training, we train model to predict a table in multiple orders, and thanks to that, order doesn't matter for our model in prediction step. But let's take one step deeper. So how does it work in terms of language model? Because I've shown some tables, but models in fact do not see tables, they see prompts. And what we can see here, we see some HTML-alike representation of a table on blue. So there are two cells already filled. So circle and triangle are already filled. There is table name, table headers, special tokens which define layout of a table, and we've got the same table in human readable form on pink in pink. So it's the same. So we more or less we represent our table in HTML-alike form, but with our special tokens, which are in our models dictionary. And you may ask, how do we create this template? Because we know what we want to extract, so we may know the name of table, we may know the columns, but how do we know the number of rows? And that's very simple. We just use regression head to predict number of rows. And we train the regression head as well. So another part of our contribution is positional encoding. So we use as a backbone a T5 model, which is language model which uses relative positional encoding. So it encodes positions of tokens in relation, using relation between them, so distance between two tokens. And as we have got a table, we instead of using distance between tokens in this HTML-alike representation, we use distance between cells. So we use distance between rows, distance between columns. We've got a special term for representing distance to header. So each token has, let's say, shorter path to attend to a header. So it's easier to use a header when predicting some cell. We use sequential bias, just plain T5-like bias as well, but we use it just within a cell. So tokens from different cells do not use this, do not see these other tokens like tokens from the same sequence. Each token is separated on this local sequential bias level. And now when we know how does training look like, we know what is inside the model, we may see how does inference look like. So we've got the same toy example. There are multiple toys and so on and so on. So our first step is using regression head to predict number of rows. So it predicted three rows, and then we create a template, and we are able to predict all values in the table. So we fill all values in our table, and what's cool, we may do it in parallel because it's not an autoregressive decoding. We may we may predict multiple tokens at once because using this this template I spoke before. So together with cell values, we've got their confidence scores, and we keep the most confident ones. So we keep them, and now this knowledge is fixed. So we may generate another 4 values, but now with some fixed knowledge, and we keep 2 most certain ones, and do it all over again. So voila, whole table is filled. And that's our framework. So what are our results? We compare ourselves to state of the art, but also to linearized baseline I spoke before. So left to right, top to bottom, human way of generating tables or filling tables. And we've got multiple backbones. So these are all in T5 family, but some of them encode 2D positions, so positions on a page, not in 1D manner, but 2D manner. Some of them have got graphical encoder, but what connects all our models is this stable decoder. And what we can see here, our model is on average better than the baseline, but when it's for one data set it was worse, but still difference wasn't statistically significant. So that's nice. We managed to beat the baseline up to 15 points of INLS score on one of the datasets, and we also managed to beat state of the art on one of the datasets. And one interesting thing about parallel decoding, because in the example I presented before, we kept 2 values at the time, and we may keep 1 value as well as 5 or more. So we analyzed the trade-off we've got between time of prediction and accuracy or score of our model. So what we know about after this analysis. So it vastly depends on the datasets. For some datasets where input is large, so we spent a big part of our time in encoder. The number of cells we predict at once does not matter because most of the time we spend in encoder. But for some datasets where input is short but table is big, this impact is way bigger. But what's interesting in terms of score, there are also some datasets which are greatly affected by generating tables in larger amount at once. So we assume that for some datasets, the cells are very correlated. And when they are correlated, when we keep the most certain one, we may use this knowledge to extract another one and so on and so on. So this knowledge we keep from fixing these cells with highest confidence later on pays itself, so it gives us higher results. But for some datasets, we may as well speed up our prediction by predicting multiple cells at once. So to wrap it all up, what we propose is training, which is permutation based and depends and randomly samples table in each epoch, together with a data-driven confidence-based decoding mechanism, and it all gives a document-to-table framework which may be applied to any encoder-decoder framework and with some slight modification to decoder-only models. And that's all. Thank you very much.
Okay, great. Thank you, Michał. Time for questions. Yes.
Thanks for a really cool presentation. Got two questions. So first, the shorter one. Obviously the examples you provided are easy
examples.
for, yes, toy examples, but I can imagine that data in real life can, be need more dimension than two, or actually can be like, time dependent. So have you tried using this? It's not about metrics, but just to see the outputs with some like more complicated documents. What's the output? Because that's actually something I'm really curious about.
You say more complicated documents or more complicated tables, or I don't know, tensors with multiple dimensions?
Let's say that the input to your model is, for example, Konstytucja Rzeczypospolitej Polskiej. What will be the output?
So it depends because it's a framework, yeah. So we may train a model to predict we may train model to do different things, like relation, like entity and relation recognition. So for instance, I don't have, unfortunately, the laser doesn't work, but here Deutsche Welle. These are news from German newspapers. And we extract people and entities from this paper. So for instance, Jacques Chirac, France, president of. It's one of examples from these data sets. And the state of the art is very specific model which is created just for this problem. And our model was able to be nearly as good as their model, but it's way broader. So it's able to tackle many different.
But it still does need some sort of like domain-specific pre-training, as I understand.
Fine-tuning.
Fine-tuning. All
Yeah,
right.
it
All
needs.
right. Thanks. And the second question is, super cool that you work with tables. That's very underrepresented area of research. I only recently discovered PyTorch Tabular, but there is not much behind. So is this like, is the code publicly available maybe?
Unfortunately not.
Oh, shudder.
I'm sorry.
All right. Thank you very much.
All right. Do we have more questions? There was one question, I think. No? The same? Okay. All right. Last chance.
Thanks for presentation. So you mentioned small and large documents. What is small in your context, and what is a large one?
So the largest context we consumed was about 8,000 tokens, and the shortest, I don't know, about 1,000 tokens.
Thanks.
Okay. Do we have more questions? I think we have time for maybe one more. All right. So let's thank once again Michał for the great presentation, answering our questions. Thank you, Michał. And now another Michał, our first speaker.
Good evening, everyone. My name is Michał Daniluk. I work at Synerise as a staff AI research engineer, and I'm super excited to be here and to give you a presentation about BaseModel. BaseModel is our platform dedicated to behavioral event data. So agenda for today is as follows. First of all, I will give you a brief introduction to behavioral modeling. Behavioral modeling is an approach for better understand and predict customer actions. It relies on vast amount of data, which is generated by customers' interactions every day. Then I will present BaseModel, our platform to dedicated to behavioral modeling, and finally I will try to give you a clear understanding of how does it work under the hood and give you some technical details about our models. So first of all, what is behavioral data? How does it look? So here it is a simple snapshot of this kind of data. On the screen, you can see some data from the e-commerce and some transactions data. So we have 3 transactions between some client ID and some product ID. Each row represents a single transaction, and each column is an attribute that it is associated with each transaction. For example, price. And usually we have also a lot of metadata and static attributes. For example, attributes per client, like age, sex, city, or many more. But usually data is very diverse, and there are a lot of sources of this kind of data. So in the context of retail, we might have web interactions. For example, page visits, transactions, product searches, product returns, add to carts, and many more. We also have offline interactions. We have also a lot of interactions from mobile apps, like clicks, scrolls, push events, and many more. We have also this kind of data in many different sectors. For example, in financial sector, where we have transfers between users, we have credit card payments. In telecom sector, we have phone calls between users, text messages, and many more. Additionally, we have, as I said, static data. For example, product attributes. We have title of the product, brand, category, image, and many more. And I would say that this diversity is not only the challenge in terms of processing such huge amount of data and analyzing it. I think that it is a big opportunity because every data point, every interaction, every attribute is a piece of the puzzle in understanding customer behavior. So nowadays, the majority of researchers are working on developing some models in the field of text, image, video. And we can answer a question, why? And the answer is simple, because AI development is driven by data availability. So for example, text data is everywhere. Let me introduce the concept of foundation model, because it's quite important in the rest of my talk. So for the text, we have a foundation model, which is, for example, GPT. And then you can fine-tune this model to have ChatGPT for a more specific task. And BaseModel aligns with these concepts of these large models, but it has 2 main distinctions. First, it operates on behavioral event data. So in behavioral event data is much richer data. So there are not only images, not only text, but interactions between some entities. And the second distinction is that we train a private foundation model. So our models are exclusively trained on single customers' data. And let me introduce and let me explain how does it work in a simple terms. And yeah, so what are foundation models? Foundation models are usually trained, they are usually very large and trained in a self-supervised way. They are trained in order to have to understand data, and they are trained in order to compress data in a meaningful way. For example, GPT is trained to predict the next token in a sequence, right? So let's imagine that we can encode all your previous interactions, all your previous behaviors. So for example, what did you buy? Or what did you visit? Or what posts did you like on Facebook? Or what users do you follow? We can encode all this information into a simple, very efficient data structure, which is called universal behavioral representation. This data structure, we can reconstruct even all previous behaviors of given user using this single vector, this single universal behavioral representation, and pretty accurately. And this universal behavioral representation is fed into neural network, and as output, as target of our training, we have this very similar universal behavioral representation of user, but that one that represents future actions for given user. And in the next part of this talk, I will try to explain how to create this universal behavioral representation and how does it work. But the main idea is as follows. As input to the network, we have some representation of a user that represents his history, and as output, we have this representation of the user that represents his or her future. Once we have this foundation model, we can easily fine-tune it for any specific business problem. For example, some regression problem. We can train a model that predicts how much money will some user spend in next 30 days, for example. Or classification model. Will I buy a hot dog in next 24 hours? Or any kind of problem you can solve. All right, and last slide before going into technical details, I would like to share with you some our success stories. So we participated in several very prestigious machine learning competitions, and we were always on the podium, and we competed with Google DeepMind, NVIDIA, Baidu, Intel, and with the top universities in the world. So, and all these competitions were based on behavioral data. For example, Rex's Twitter challenge, the goal was to predict interaction between some client and tweet. And the data set contains 1 billion historical tweets. There are two main distinctions between our solution and our competitor solutions. First of all, we use the same architecture, the same models for each competition, compared to our competitors, which used very custom, handcrafted models to each competition. The second distinction is that our models are very fast. So for example, at the Rex's Twitter challenge, we are able to make a prediction in 6 milliseconds using only single CPU. For KDD Cup, we are able to make a predictions for the whole test set in 7 minutes compared to DeepMind solution, which requires 12 hours. All right, so how does it work? So our models are not based on any open source models or closed source that you can buy. We developed everything from scratch in our team. And the first part, the first piece of BaseModel is Cleora. Cleora is a nice software package that we made open source, and it takes as input a graph and produced some very meaningful embeddings for each node. And let me explain a graph concept. Let's say that we have some e-commerce and we have some interactions between users and products. So we can create a graph where each user and each product is a node in a graph. And we have some interactions between nodes. So for example, I buy some specific product and I have an edge between myself and this product. And this graph, you know, there is a lot of very meaningful information in this kind of graph, and it is very common in a lot of areas, like for example retail. And the goal is to take this graph and produce some very meaningful embeddings for each node. For example, here we have a graph with 5 nodes, 2 users, 4 products, and Cleora takes this as an input and produce embeddings per each user and per each product. And the idea is that similar products have similar embeddings, similar users have similar embeddings. This model is trained in a fully unsupervised way, so we don't need to have any labels. Right, and Cleora is only the one part of our tech stack. There is a lot of more behind the scenes, and MD is a crucial part of that. It is very important. MD is a mathematical model that is designed for a very special purpose. It is designed for creating these universal behavior profiles, which I have mentioned you a couple slides ago. So MD stands for Efficient Manifold Density Estimator. And what is the goal? The goal is that we can take some set of vectors. In this example, we have 3 vectors, and we want to convert them somehow to some data structure which has a fixed size. And why it is useful in retail or any kind of event data? Because, for example, you want to represent our history from some e-commerce. And for example, I bought some 3 products. Each product is represented by some embedding. And we can represent somehow these 3 embeddings in a fixed size structure, which is called sketch, that can be then fed into neural network. And the idea is that the number of input vectors may be very different. I bought, for example, 3 products, but you may buy, for example, 100 products. And we want to somehow encode all these vectors into a data structure which is called sketch. And how does it work? All right, so let's imagine that I am a user and I want to create my universal behavior profile. And let's say that I have an interaction. I had the interaction between 2 products. I bought Adidas Slick shoes and Adidas Nova Motion shoes. Each product in this scenario is represented by 3 modalities. The first modality is text modality. So for example, description of the product. This text embedding is generated by some transformer-based model. The second modality is image modality, and the embedding is also generated by some transformer-based model. And the last modality is interaction modality, which is created by Cleora, our graph embedding method. By the way, this is inspired by, this actually incorporates a technique which is called locality sensitive hashing. And how does it work? So let's imagine that we have that those vectors are 2-dimensional and they are represented by these red dots. So this text embedding is represented here by this red dot. We divide this item embedding space into some regions. And how to do it? There are a couple of ways, but let's say for the beginning that we can create random hyperplanes, so random blue lines that divide this space into some regions. And the first product, text modality, goes to 0 bucket. So then we can create a structure which is called sketch, that it is one hot structure. At the 0 position we have 1, everyone else we have 0. And the same with other modalities and the same with other products. So here image embedding goes to the 3rd bucket. At the 3rd position we have 1, everyone else there is 0. And the sketches of individual products are then aggregated by simple summation to create a sketch that represents all products in a history, right? So this modality and this modality as is aggregated, we have 2 and zeros, everyone else. And the idea is that similar embeddings are in the same bucket. Yeah, and there are many questions. For example, how to create these blue lines, these hyperplanes that that make this division. So as I said, you can do it randomly. You can do it in more clever way. Actually, it is a quite active area of our research. So, for example, you can do data dependent. So, where we have more vectors, we may have more hyperplanes, for example. Right. And then we have this universal behavior profile for this simple, very simple case where we have just 2 products as an input. And as you can see, I can have more products, and then there are just summed and fed to the network. Yeah. All right. So that's the main idea of MD. We released a paper about that like 2 or 3 years ago. We tested it on the recommendation setup, and we achieved state-of-the-art result. All right, so that's it to summarize. So we have developed a world-class technology. We use this model in our platform. So for us, it is very important to provide real-time predictions. Our solutions are scalable. So we have clients with billions of interactions, millions of users, and thousands or millions of products. We open source a lot of our models. So Cliora is open source model. We also open source code for our solutions to competitions. We also have a lot of internal improvements that are not open source. We have published a lot of papers that were accepted at the top tier conferences. If you are interested, I encourage you to read more about what we are doing at our research blog, to play with the open source version of Cliora. And recently we released Cliora Pro. Cliora Pro is a better version of Cliora with some graphic user interface where you can upload a graph, and as a result, we received vectors per each node. And finally, we are looking for talented people. So if you are interested, you can send me an email or we can talk after that. Thank you very much.
All right, time for questions. We have the first question.
Thanks for the presentation. Again, I have 2 questions. First one will be more about research, the second about engineering. So when you told about this, like finding good partitions for the manifold, maybe that's a naive idea from my side, but when you told that you are like, doing it randomly at first, I immediately seen that something which is like parallel to like evolutionary computing with some sort of a like fitness function next step. Have you tried to explore this idea? Or this is maybe something completely wrong? I don't know. But
all right, so so the question is if it is computationally efficient, or what is the question?
No, I mean, I'm interested on how you actually put those blue lines.
Right.
I mean, my initial idea was about like
Right.
evolutionary computing, but maybe there's something smarter.
Yeah. All right. So you can, first option is just to do it random, right? But the problem is that there might be some buckets that doesn't have any vectors. So let's say that we have 100,000 images in your dataset. So they have 100 vectors. So instead of dividing in randomly, you can have more hyperplanes, more hyperplanes, more divisions in the place where there is a bigger density of embeddings. So let's say that here we have a lot of embeddings, and here we don't have a lot of embeddings, right? So here you have more divisions. So it is a data-dependent division. So in other words, in the places where we have more products, more embeddings, in those places there are more divisions. Yeah, and by the way, this step you can do it offline. So you can there is a single step. There is a first step before training the model. So before training the model, you can have all these divisions. And then when you want to train a model, and then when you want to create this behavioral profile of a user, you can do it on the fly. You can keep in a memory only these vectors, and you can do it before training.
So will it help you to have a good density estimator, like I don't know, the networks? I mean, will it like massively help with this problem?
Can you say again, please?
If you will have something like a density estimator in this like manifold, will it help you?
Yeah, this data dependent, this density estimator, yeah, it helps. If it is a data dependent, we have a better results.
There is this quite recent paper from Steintrug et al. About, I mean, it was for images like stable diffusion, which are actually quite good and estimating intrinsic dimensions. So maybe it's a kind of parallel to your problem.
Okay.
And the second question, so you told that there is Cleora and MD, but I missed one part. So how do you get the graph? Let's say that we got, I don't know, a client who want to do some CTR or this kind of problem, and obviously there's stateful, all that kind of data. I missed the part how to construct a graph.
Okay, so BaseModel is able to connect to many databases. For example, we are able to connect to Snowflake, BigQuery, and many, many more. And then you need to define and then actually you need to define the main entity in a graph, and usually the main entity is a client. And then we make a graph between this client and any column that has enough distinct values.
That's like a knowledge graph building. Or not really?
Yeah, not really. So let's say that we have a columns in a database, client and product, and that's it. Let's say the simple example. So we know that we have a lot of products, we have a lot of distinct values of products, and we automatically create a graph. And so what we did actually behind the hood, behind the scenes, is that, for example, we just group by a client, and then all products that belong to the client create one edge, one hyper edge for all those products. And yeah, that's basically it.
All right. Thank you very much.
Thanks.
Okay, we have more questions.
Thank you. That was interesting. I'm interested in how much data per user do you need to have like accurate enough predictions?
Well, per customer you're asking, right?
Yeah.
All right. So so the answer is simple. The more data, the better models are. So of course, and I don't have in mind any specific number right now, but I would guess that we need at least couple of thousands of interactions, right? But it is the minimum to have. I think the minimum is to have, let's say, 50,000 of interactions for a given user. So if you are e-commerce that have only thousands of interaction, it's very difficult to train something with this kind of data. But usually we require at least 100,000 interactions, let's say. But it is, it just is I don't have a specific answer for that. But yeah, the more data. Usually our clients are, for example, from the e-commerce sector. In e-commerce sectors, for example, you have page visits, you have transactions, and page visits are, every milliseconds you have some page visit. So usually this data is very, very huge.
Thank you. Just one more question. Can the model be used to predict different type of events, not the customer events, but different types?
Of course, yes. For example, okay, so we can predict anything about any entity in a data set. And usually the main entity usually is a client, a single person. But it can be, for example, credit card or cookie in online session, something like that.
Can you predict, for example, a patient data like medical data, or this model isn't for this?
Can you elaborate on that? Like, give you an example?
Just an idea, but for example, you have got the patient data, like for example, some health parameters, some events that this patient performed, for example, on the clinic, and you have got like a lot of data for a lot of patients. So, do you think this model can be used for this kind of event predictions?
Yes, of course. So actually, yeah. But again, in this case, you have some data about user and some, let's say, interaction. Okay. We need to have, okay, and I will answer in other way. We need to have some interactions between, for example, two entities. And the user and product, this is just an example. And we need to have these interactions at some timestamp. So we need to have these events. In a medical setup where you have just a client and some attributes for clients or some, I don't know, some health issues. So it is not this case actually.
Okay, thank you. I love it.
Thank you.
Good. So we have at least 2 more questions.
I have a question regarding this manifold partitioning step. The way I see it, it aims to transform the upstream representation, the embedding, into another form, which you then add together.
Yes.
And then pass forward. Why don't you just add the embeddings or use some machine learning based method to reparameterize the embedding in a form that you could use later on?
Well, so the first question, why we don't use just embeddings? Okay, so the simple solution might be just to take the average of those two embeddings, text embedding and text embedding of the second product, right? It can be a simple solution, just take an average. But it doesn't work because we lose a lot of information by averaging them. That just because, right? We lose a lot of information just taking average of all your products. And in this idea, you have these sketches that represent it. And we have these one hot vectors, but it doesn't need to be one hot actually. And for example, okay, we have, let's say, these one hot vectors, and then you can just sum them and think about that as a histogram. It is a histogram-like structure that collects all your data, all your, let's say, products. And it just works much better than taking, for example, just simple average of all embeddings.
Okay, so a follow-up question. Why not use the machine learning method to reparameterize the embedding space into the form that would bear some meaning when added up or averaged?
I'm not really sure on what. I mean, I'm not really aware of these machine learning methods. I don't. What type of methods do you mean?
Well, what are you doing here? As I see it, it's just transforming a vector into another vector, and then you add them later.
They have a very nice structure that can be, they are additive, right? These vectors, and it is the reason.
Okay, thank you.
Thanks. Right. Yeah, and the idea is that actually it doesn't need to be one hot. For example, we can say that we spent $1 on these shoes and $100 on these shoes. So instead of just one, we can put one here because we spent $1 on these shoes, and on these shoes we spent $100. So we can put 100 here, and then we have a stronger interaction for let's say more expensive products, for example. So it doesn't need to be one hot, but just in this simple example there is. And of course, then when you put it to the neural network, then you need to L2 normalize each sketch, but it is a technical aspect.
Okay, good. I think there's one more question, so this will be the last one. Okay, we'll see.
Yeah, first of all, thank you for the presentation, and that was great on vectorizing and tokenizing to put it into the model. And simple question then, what is the size of the model you use as this feed forward? And if it varies for the clients, you can give just order of magnitude for particular clients if possible.
Okay, so what is the size of the model, and how what is this fit for a neural network? So it fits on a single GPU. It fit for a network, but a little bit more complicated fit for a network. It is not, just a basic fit for a network. It has some residual connections, some layer normalizations, etc., etc., and it has several layers. Usually, it is between 4 and 6 in our experiments, and the size of the model is it depends. So it is configurable, so you can set a hidden size whatever you want, but usually it requires like between 30 and 60 gigabytes of memory, so it fits on a single GPU. No, just fit for a network. It is the input. We have some residual connections, some layer normalizations, but it is just fit for a network. Yeah.
All right, Michał, will you stay with us for the after
course,
party?
yeah.
Okay, so we can maybe allow the last question. Yes, you want to ask? Okay, but really last one.
Thank you. This is like one of the crazy questions. Have you been thinking maybe about some experiments to feed this architecture with huge amounts of real-world data and trying to predict real-world events? Or, for example, as I said, I'm not an engineer, but this is like a crazy question. But I think it could work in some cases, and it could give crazy results. What do you think?
I'm not sure on what real data are you talking, like
for example, you have got some stock exchange, some stock company, and you create two entities, company and world events, and you first feed the model with previous data, and then you try to predict how the stock behaves, like one of the examples.
Yeah, I think it's a very interesting idea. I will think about that. I just want to add that you can add as an input to this network, you can add anything you want here as an input. You can just concatenate. And you can add, for example, some information, somehow encode it, for example, recent events or recent weather or recent, for example, year, and we can make a different prediction per different month, per different day. So what I just want to say that we can incorporate a lot of knowledge, additional knowledge as an input to this model, just a simple concatenation with what we already have. Yeah, but I'll think about that. Yeah, thanks.
Good, thanks. Thanks for the question. Michał, thank you once again.
Thank you.
Okay, so that was the last talk for today, but we hope you will stay with us for the after party and you can ask some other questions to our great speakers. And that's all. We hope you enjoyed this event, and let's have fun together during the networking part. Thanks. Thank you.